Hello and welcome to the Week 8 Math 2419 review. This week we'll be covering differentials, chain rule for functions of several variables, and also directional derivatives and gradients. Let's go ahead and jump right in with some differentials. So, if you recall, when we write something like dx, well, this means either the derivative with respect to x, but it can also mean a small change in x. And this is actually what we're interested in, because frequently with functions of one variables, we would write change in y with respect to the change in x. Alternatively, we could write that the change in y is based off of some function of x times the change in x. And this is the idea behind differentials. So we can define what's called the total differential. And that would be our change in z is equal to the slope with respect to x times our change in x plus the slope with respect to y times the change in y. And of course, this is for function z is a function of x and y. And in essence, what we're saying is that very small changes in z can be calculated using a very small change in x and multiplying by the slope in the x direction, and then adding small changes with respect to y and multiplying by the slope in the y direction. So specifically, if we had actual changes in x and actual values for our change in y, we can use this to get an actual change in z. So let's go ahead and do an example, kind of illustrating this concept. Let's say you have the function z is equal to 3x squared y minus 2xy cubed. And first off, let's just really quickly find the total differential. The total differential, remember, is the derivative in the x direction, or the derivative with respect to x, which would be 6xy minus 2y cubed times dx, plus the partial derivative with respect to y is 3x squared minus 6xy squared dy. Finish off our total differential. Here, I'll just make a note of that. Now let's say we wanted to approximate z at the point 1.1, negative 0.1. Well, this point is very close to the point 1, 0, and in fact, there's only a slight change between them, and we can actually define the slight change to be a change in x of 0.1 and a change in y of negative 0.1. And this value, this delta x, I got from taking the actual x value, or the approximated x value, 1, and seeing what kind of change would need to be added to it to get our exact x value. So 1 plus 0.1 gives us 1.1. Likewise for the y value, 0 minus 0.1 gives us negative 0.1. Well, then we can approximate our change in z from this point 1, 0. And our change in z would be based off of this total differential here. It would be 6xy minus 2y cubed, and importantly, we use the values of our approximate point here in order to estimate this. So 6 times 1 times 0 minus 2 times 0 gives us 0 times 0.1, which is our delta x, plus 3 times 1 squared gives 3, minus 6 times 1 times 0, so 3 times negative 0.1 gives us a delta z value of negative 0.3. And importantly, the z value at 0.1 comma 0 is equal to, well, that would be 3 times 1 squared times 0 minus 2 times 1 times 0 gives 0. We can say that the z value at the point 1 comma 0 is about equal to, or sorry, the z value at the point not 1 comma 0, but at 1.1 negative 0.1 is about equal to the z value at the point 1, 0 plus this change in z. If you wanted to think about it with a kind of two-dimensional or a single variable perspective, what we're doing is if we have basically some curve here like this, and we wanted to approximate, or if we know the exact value at this point and we wanted to approximate the point, let's say right here, well, all we're doing is we're taking the tangent at this point and trying to calculate essentially this point here, because we know that it would be very close right there. And this would be the actual error. But this point here is very close, and this is our approximation. If this is our z value, this would be z plus delta z here. So when we take our actual point and add our delta z, we get 0 plus negative 0.3 gives us negative 0.3 as an approximation for z at 1.1, negative 0.1. And the actual value is negative 0.3608, so we're actually fairly close. We're only about 6/100ths off. So it's a fairly good approximation, all things considered. Okay, let's go ahead and do a practice problem. Find the total differential and then use it to approximate the function at the given point. And the function will be f of xy, think of it as z being equal to f of xy, is e to the x times y plus y squared at the point 0.1, 0.9. And I'll give you a couple of minutes to work on that. All right, let's go ahead and go over this problem. So first off, to calculate the total differential, say that dz is equal to the derivative with respect to x, which would be e to the x y times dx. That's not dx. Should be dx though. Plus the derivative with respect to y is e to the x plus 2y times a change in y. So this is our total differential. Next up, we need to figure out which point the given point is closest to. So we can say that 0 0.1, 0.9 is really close to 0, 1. Now, importantly, when we plug in 0, 1 for f, we get that would come out to be e to the 0th is 1 times 1 plus 1 squared gives us 2. Next, we need to calculate our change in z, which would be equal to e to the x times y. So e to the 0th is 1 times 1, 1 times delta x. In this case, delta x would equal positive 0.1 because from 0 up to 0.1 is a change of positive 0.1 plus e to the 0th plus 2y gives 1 plus 2, so 3 times our delta y. Delta y in this case from 1 down to 0.9 is a change of negative 0.1. This gives us 0.1 minus 0.3, which is negative 0.2 as our delta z. So we can say that f of 0.1 comma 0.9 is approximately equal to f of 0 comma 1 plus delta z, which is equal to then 2 minus 0.2, so 1.8. So our approximation, or f of 0.1, 0.9, is 1.8. All right. Do one more example problem that's going to be a bit different. Let's say we have a box and it has sides of 2 meters, 1.5 meters, and 2.5 meters. And when you measure the sides, there's a possible measuring error of 0.01 meters, so of 1 centimeter. Then we are asked to estimate the maximum error in calculating the volume. Okay, so because we're calculating volume, we'll want to figure out our formula for volume, and that is, of course, length times width times height. Well, this is actually a function of 3 variables, so in order to calculate our total differential delta V, we would need to take 3 partial derivatives. First, the partial derivative with respect to L gives W times H, and then delta L. So this is our partial derivative with respect to L times delta L. Next, our partial derivative with respect to W is LH, and then we multiply by our change in W. Finally, our partial derivative with respect to H, multiplied by our change in H. All right. So then, simply plugging in our values of, we let 2 be the length, 1.5 be the width, and 2.5 be the height, Well, then we know that our possible error is 0.01 meters. This would actually be equal to the change in the possible error in the length, or the possible error in the width, or the possible error in the height. And they're all equal to 0.01. So from here, we have found all the components necessary to calculate the possible error in V. First, our width times our height is 1.5 times 2.5, multiplied by 0.01. Add length times width, length times height, times 0.01. And again, length times width is 2 times 1.5 times 0.01. Overall, this gives us a possible error of 0.1175 cubic meters as possible error in measuring the volume. Perfect, perfect. All right, let's go ahead and move on then to the chain rule for functions of several variables. The chain rule is something that some students get tripped up with. But once you get used to it, it's really not all that difficult. So let's say you have a function w, and it's a function of both x and y. But then in turn, x is a function of t. We're going to use g of t. And y is also a function of t. We'll call it h of t. Well then, clearly we can calculate the partial derivatives of w with respect to x, and also the partial derivatives of w with respect to y. But since w is based off of x, and x is based off of t, w is also kind of based off of t as well, which means we should be able to calculate the derivative of w with respect to t, right? And we actually can. The way we do that, though, is through the chain rule. Basically, we say, well, I can calculate the derivative of w with respect to x, so I'm going to do that. But then I know that x is in turn based off of t, so I need to calculate the rate of change of x with respect to t. So then I've calculated the rate of change of w with respect to x, then with respect to t, and this I call my rate of change of w with respect not quite to t yet, though, because in this case, y is also based off of this variable t. So I need to include that in my calculations as well. This is how I define change in w with respect to t. The easiest way to think about this is I looked at all the variables that were dependent on t. In this case, it turned out to be both x and y. And then I calculated the partial derivatives with respect to those variables x and y, and multiplied by their changes with respect to t. It can be helpful to draw tree diagrams to do these. So for example, function w is based off of x and based off of y. Then x in turn is based off of t, and y is also based off of t. So following this pattern, if we take the derivative with respect to x, we can then take the derivative with respect to t. And then this is based off of t. Also, this is based off of t. So then everything based off of t together would be dw dx, dx dt plus dw dy, dy dt. It can get a bit more complicated. So, for example, if we still keep our w is equal to f of x and y, then instead x is a function of two variables, t and s, and y is then a function of two variables as well, also t and s. Well, then we still need a way to calculate the derivative of w with respect to t, or with respect to s. Again, a tree diagram can be helpful. If we start off looking at just w, we can take the derivative with respect to x, or with respect to y. From here, though, if we took the derivative with respect to x, well, now we have the option of taking the derivative with respect to t, or with respect to s, sorry. And if we take the derivative with respect to y, well, now we can take the derivative with respect to t, or with respect to s as well. And this would give us change in w, change in y, change in y, change in t, that should be y ds, that's what it should be. And here we have dx, w dx, dx t, and finally dw dx dx ds. And to calculate the change in w with respect to t, we simply identify everywhere we took the derivative with respect to t and add all of those components up. So in this case, we have change in w with respect to x, dx dt, and also dw dy, dy dt. So we could say that change in w with respect to t is dw dx dx dt plus dw dy dy dt. And similarly, if we wanted to calculate dw ds, well, that would be dw dx dx dy, not dy, ds, plus dw dy dy ds. Yep. So let's go ahead and do an example. Find dw t and dw ds of w is equal to x squared y plus xy squared, where x is equal to 3t minus s and y is equal to 3t squared s. Well, in order to find partial of w with respect to t, I simply identify all of my functions that are dependent on t, all of my variables that are dependent on t. In this case, I notice that my x has a t in it, my y also has a t in it. So both x and y are dependent on t. Because of that, I know that I'm going to need to take the derivative of w with respect to with respect to x, and multiply by the derivative of x with respect to t. And then the derivative with respect to y, and multiply by the derivative of y with respect to t. Well, when I do that, dw dx would be 2xy plus y squared times the derivative of x with respect to t is simply 3. Next, we add change in w with respect to y, dw dy. We get x squared plus 2xy multiplied by change in y with respect to t, which we get 6ts. However, if you'll notice, now our answer has xy and t and s in our answer, and that is not great. So what we'll try and do is we'll substitute out all of our x and y's, because remember, our derivative is based off of t. We've got change with respect to t, so we'd like to keep t's and s's in our solution. So we'll substitute out all of our x and y's using these two equations right here. And we get 2 times x is 3t minus s times 3t squared s plus y is 3t squared s squared times 3 plus x squared is 3t minus s squared plus 2 times 3t minus s times 3t squared s times 6ts. And I am not going to bother simplifying that. However, it is important that you substitute out your x's and y's. All right, next up, we need to calculate change in w with respect to s. Once again, we look back and identify which of our functions are dependent on s. In this case, it would be in a different color. There's an s in the x function, there's an s in the y function, so both x and y are dependent on this variable s. Because of that, we need to calculate change in w with respect to x, then change in x with respect to s, and add dw, dy, dy, yes. All right then. Change in w with respect to change in x, if you recall, I'll go ahead and scroll up, was 2xy plus y squared. Change in x with respect to change in s, well, that would be derivative of 3t minus s with respect to s is -1. Next, change in w with respect to y is x squared plus 2xy multiplied by change in y with respect to change in s gives us derivative of 3t squared s is just 3t squared. Once again, we now have these x's and y's in our answer. We don't want that. You need to substitute out. And 2 times, oh boy, let's see if I can remember what it was. 3t minus s times 3t squared s plus 3t squared s squared times -1 plus 3t minus s squared plus 2 times 3t minus s times 3t squared s all times 3t squared. And that would be our derivative of w with respect to s. All right. That would be the solution. Now I'll go ahead and give you one practice problem. Go ahead and find dw dt and dw ds for let's say w is equal to x squared times 1 plus y, and x is equal to sine of t plus s times, and not times, y is equal to 3s squared. I'll give you a couple of minutes to work through that. All right, let's go ahead and go over the solution. So, we can write dw dt. Well, we can find change w with respect to x, which would be 2x times 1 plus y, then multiply by the change in x with respect to t, which is cosine of t plus s. Then we need to add the derivative of w with respect to y, and multiply by the change in y with respect to t. Notice that y is independent of t, so that would come out to be 0. So 2x times 1 plus y cosine of plus. We need to substitute out our x's and y's. So changing w with respect to t comes out to be 2 times sine t plus s times 1 plus 3s squared times the cosine of t plus s. Next, we look at change in w with respect to s. Well, again, we calculate change in w with respect to x, and we get 2 times 1 plus y multiplied by change in x with respect to s, that is cosine of t plus s, Then we add change in w with respect to y, which is x squared multiplied by 6s, which is dy ds. Again, substitute out our x's and y's, and we get 2 sine t plus s times 1 plus 3s squared times cosine of t plus s plus sine squared of t plus s times 6s as our final answer. There we have it. Okay. Last up, we do have a couple of rules for implicit differentiation. So let's say you have a function f of x, y, z, and it's equal to 0. Or in other words, we could have like z being declared implicitly in terms of x and y. Well, then let's say we wanted to calculate change in z with respect to change in x. How do we do that? Well, as it turns out, it's fairly simple. I'm just going to give you the rule for it. We take the partial derivative with respect to x and place it over the partial derivative with respect to z. I'm not going to go into why this is the case. You probably mostly care about that it is the case, but an easy way to remember it is that the opposites will match. You'll notice z on top on the left results in z on the bottom on the right. And likewise, x on the bottom on the left is x on top on the right. And you just need to include this negative sign. And this is the same case for any partial. So if you wanted to find instead change in y with respect to change in z, all you do, make it negative, flip it. Sorry, that should not be an x, that should be a z. Or change in x with respect to change in y, negative f sub y over f sub x. So, if we did one quick example, we have x squared y plus 3z y squared is equal to 0. Well, then we can calculate dz over dx by simply calculating negative f sub x over f sub z, which is derivative with respect to x would be 2xy. Again, we need to keep our negative out. Divide by the partial with respect to z, which is simply 3y squared. And when we simplify, we get negative 2x over 3y. For one other quick example, let's say we have f of x, y, z is equal to 2x y, z, and that's equal to 0. Well, then change in x with respect to y would be negative f sub y over f sub x. So that would be negative 2xz over 2yz, which is equal to negative 2x over 2y. So just negative x over y. Cool. Let's go ahead and move on to the last topic, which is directional derivatives. And gradients, of course. Okay. So, if you recall, let's say you have a function f of x, y. Well, we can call the derivative with respect to x the slope in the x direction. We could call the derivative with respect to y the slope in the y direction. But what if we wanted to find a slope in a different direction? What if we wanted to find the slope, let's say, halfway between the x and y direction? Well, the way we do that is through directional derivatives. And we indicate the direction we want to take the slope in using a unit vector. So one thing you might see is like slope of the function f of xy is equal to 3x squared e to the 2y in the direction of this vector 1 over root 2, 1 over root 2. And you'll notice this vector 1 over root 2, 1 over root 2 is a unit vector. It has a magnitude of 1. That's important. So we can find our partial derivatives f sub x, which is equal to 6x e to the 2y. And also we can find f sub y, which is equal to 6x squared e to the 2y. And also we would need a point. We'll just say at 1, 0. Well, we can calculate our partial derivatives at this point 1, 0. Here we would get 6 times 1 is 6, and also f sub y at 1, 0 gives us actually the exact same thing. So perhaps this isn't the greatest of examples because we're getting the exact same thing here, but oh well. We can actually use these vector components to almost represent proportions, or how much in the x direction we need to consider and how much in the y direction we need to consider. So all we need to do is take this f sub x and multiply it by the x component of this vector. So 6 times 1 over root 2, and then we add it by our y derivative times the y component. And that would give us 6 over root 2 plus 6 over root 2 actually gives us 12 over root 2, or 6 square root 2. And this would be our derivative in the direction of 1 over root 2, 1 over root 2. Yeah. Basically, the idea behind it is we use this direction vector as proportions to tell us how much in the x direction we need to take and how much in the y direction we need to take. I prefer to think of directional derivatives in terms of the gradient. The gradient is a fairly simple concept. So the gradient of a vector f is simply a vector of all the partial derivatives. So if f is a function of x and y, the gradient would be the x derivative, comma, the y derivative. And then we can actually define the directional derivative. So derivative of f in the direction of u of some unit vector u is simply the gradient of f dotted with this vector u. So in this previous example, we could take our gradient to be equal to the x component, which is 6x e to the 2y, comma, and then the y derivative, 6x squared e to the 2y. And at the point, gradient f at 1, 0 is simply 6, 6. And then we could dot that with our direction vector, 1 over root 2, 1 over root 2. We get the exact same result. Another example. Find derivative of f of xy equal to x cosine y in the direction of this vector 5, 12 at the point 2 comma pi over 3. Perfect. Well, we know that our directional derivative is the gradient dotted with a unit vector. So first off, we need to find the gradient of f, and that would simply be the derivative with respect to x gives us cosine of y, derivative with respect to y gives us negative x sine y as our gradient vector. So of course, if we evaluate that at our specific point, 2 comma pi over 3, that gives us a vector of 1/2, and then negative 2 times square root 3 over 2 is negative square root 3. Next, we need to find out what our unit vector should be. 5 comma 12 is not actually a unit vector, so we need to make sure its magnitude is equal to 1. However, I can recognize this as a special 5, 12, 13 right triangle if I drew it out. 5, 12, 13. I know I switched the sides, but the x and y sides, but I don't really care. I know that the magnitude of my vector is 13, so to normalize it, or to get its magnitude down to 1, I can just divide all the components by 13. And there is my unit vector. So then my gradient, dotted with my unit vector, is simply 1/2 comma negative square root 3, dotted with this vector 5 over 13, 12 over 13. And that gives 5 over 26 minus square root of 3 times, I'm going to go ahead and multiply by 2 on top and bottom, so I have 26 on top and bottom. And I can combine these to get 5 minus 24 root 3 over 26 as my answer. Okay. A couple of practice problems. Here's one first practice problem. Find derivative of, give you a function of 3 variables, x, y, and z, equal to x, y, e to the z, in the direction of this vector 1, 2, 1, at the point 2, 3, 0. And just remember, since you have 3 variables, your gradient will be derivative with respect to x, derivative with respect to y, comma derivative with respect to z. However, your directional derivative should still be the gradient of f dotted with your unit vector. Actually, I'll go ahead and write down the second practice problem. Find the direction of maximum and minimum increase of f of xy equals to 2x squared y at the point 2, -1. I'll give you a couple of minutes to work through those. All right, let's go ahead and go over these. So, first off, if we calculate the gradient of this first function, we see that the derivative in the x direction would be y e to the z, then x e to the z is the y derivative, and finally our z derivative is x y e to the z. Back at the specific point 2, 3, 0, we get a gradient of 3, 2, 6. Next, we need to calculate out what our unit vector should be. And we can say it is our original vector 1, 2, 1 divided by the magnitude of this vector 1, 2, 1. The magnitude of this vector would be magnitude of 1 plus 2 squared plus 1 squared. So that would be on the bottom square root of 6. So 1 over root 6 times 1, 2, 1. All right, then our directional derivative would just be this gradient 3, 2, 6 dotted with 1 over root 6 times 1, 2, 1. Since this 1 over root 6 is basically just a coefficient, we can pull it out front. And then we have 3 times 1 is 3, plus 2 times 2 is 4, plus 6 times 1 gives us 13 over the square root of 6 as a final answer. All right, for this final problem, we need to figure out the direction of maximum and minimum increase of f of x, y. First off, let's calculate the gradient. That's that would be 4xy, 2x squared, and at the point 2, 1, 2, negative 1, we get a gradient of negative 8, 8. But how do we determine the direction of greatest increase? Well, we can actually figure this out based on the dot product formula. So let's say that our gradient is one vector, and our unit vector is the other. And the angle between them will be cosine of theta. Well, then we know that that has to be equal to the gradient of f dotted with our unit vector. And we are currently trying to maximize this value here, this dot product, because that would give us the greatest directional derivative. And therefore, because the derivative is greatest, that would be the direction of maximum increase. Well, in order to maximize this, we know that the magnitude of u is just 1. So we have the magnitude of f times the cosine of theta. Well, cosine of theta is maximized when theta is equal to 0, because that would make cosine equal to 1. And when theta is equal to 0, the angle between your gradient and your unit vector should be equal to 0. In other words, they're pointing in the same direction, is when this magnitude of the gradient times cosine of theta would be maximized. So our directional derivative is largest when the unit vector is pointing, when the direction vector is pointing in the same direction as this gradient. In other words, in order to find the direction vector, we simply normalize the gradient vector we found here. And that normalizes to negative 1 over root 2, 1 over root 2. So this is the direction of greatest increase. Similarly, to find the direction of minimum increase or maximum decrease, we want to minimize the dot product. And to minimize the dot product, instead of having theta is equal to 0, we have theta equal to pi, because that would make cosine equal to negative 1, which is cosine's minimum value. The gradient of f is a constant, so that would, when cosine of theta is equal to negative 1, that minimizes our directional derivative. So when theta is equal to pi, which makes cosine equal to negative 1, then our gradient and direction vectors are pointing in the opposite directions. Or in other words, the direction of minimum increase occurs when the gradient and direction vectors are in opposite directions. We could write gradient f is equal to negative u. Well, not necessarily equal to, but some constant that is the gradient of f. Basically, they point in opposite directions. I'll just note that down. If gradient of f and u are in same direction, that max increase. And then if gradient of f and u are in opposite directions, that is minimum increase or maximum decrease. All right, and in order to find this direction of minimum increase, we can simply take the direction of maximum increase and make it negative. So that gives us 1 over root 2, negative 1 over root 2 as our direction of minimum increase. That one would be our maximum. So there's our answer, and we are done. All right, well, thank you for watching today. That's all the material for today, so have a good week. I'll see you around.